Welcome. Last time we calculated some Riemann sums to find the area of a certain region. We did that by doing the arithmetic by hand essentially. But when we are using systematic choice of points in the Riemann sum, we can use a programmable calculator or a computer to do this. You can also use a spreadsheet. I will show you how we can use built-in functions in TA83 or 84 to do the same thing. Actually, with TA84, there are two different functions you can use. One of them uses the sum function in the math menu. This is a little bit more complicated than it needs to be, in my opinion, because you have to first express the Riemann sum in sigma notation. With the TA83 and 84, there is a different operation that's found in the list menu that you can use to do this without using sigma notation. That's the one I will use in this course. It takes a little bit of work to set up in the sense that you have to tell it the starting and ending points rather than being read off from the problem. It just takes a little bit of thought, but not that much, especially if you're using standard choices like left endpoint of each subinterval, right endpoint of each subinterval, or midpoint of each subinterval. So all of this requires that you use equally spaced points. Otherwise, these calculations are harder to do and really require you to use a spreadsheet or write a program. A description of this in general terms is on slide 23. I will proceed directly to the example where it's easier to explain how to use your calculator. We will do the same region we did in our previous example. That is to say, the area bounded by the graph of y equals square root of 1 plus x squared, the x-axis, the vertical lines x equals 0 and x equals 1. The difference is that this time we are going to use 50 subintervals rather than just 5. Clearly we want to do this using some kind of aid rather than doing it completely by hand. We'll also compare the answers with what we got last time. Let's again write down the basic things we need. We are going to use 50 subintervals, so n is 50. Well, for the whole interval, the left-hand endpoint a is 0, the right-hand endpoint b is 1, the function giving the top is square root of 1 plus x squared, the step size is b minus a over n, 1 minus 0 over 50, which is 0.02. If you think about this in terms of intervals, first subinterval will be from 0 to 0.2. The left-hand endpoint is 0. The last subinterval will end at 1, so it starts at 1 minus 0.02. So when I use left-hand endpoint, first left-hand endpoint, first point in the sum will have x equals 0. The last one is 1 minus 0.02. And the step size is also 0.02. So now let's see how to do this in our calculator. We can do this first by generating the list of numbers to add and then adding them, so on. Or you can do it all at once. I'm going to take intermediate step. We will do the two list operations together and then multiply by 0.02. So first you go to the list menu, which is second step. We want to find the sum of a list of numbers. The sum operation is in the math submenu of the list menu. It's entry number 5. We are going to sum a sequence of numbers we will generate. So again, you go to the list menu. Now we want to generate our list. It's generated by using a function applied to an equally spaced sequence of numbers. So we are going to use the sequence operation on list. That's the fifth entry in the operation submenu of list menu. To do this on TA84, you put things in according to the prompt. Function expression is square root of the quantity 1 plus x squared. The variable is called x. It allows you to use different names for variables. X is the easiest to put in, which is why I always use that. X starts at 0. It's going to end at the left-hand endpoint of the last subinterval, which is one step before the right-hand endpoint of the big interval. The whole region ends at 1, so left-hand endpoint of the last subinterval will be one step before, so it's 0.02 before 1, and the step size is 0.02. If you're using a TA83, you have to put this in by hand, and this is what you will need to put in. Because if you make a mistake, you can edit it here instead of having to start all over again. This is the sum. I need to multiply it by the width of each subinterval. That's same as the step size, 0.02. So the answer we get for the Riemann sum with 50 subintervals and left-hand endpoints is 1.14367, etc. Correct to 4 decimal places, it will be 1.1437. Let's record that. If I use the right-hand endpoints, I will start at the right-hand endpoint of the first interval. It will be one step from A. In our example, that's 0.02. So I start at the left-hand endpoint of the big interval, 0, go one step to the right. It ends at 1, the right-hand endpoint of the big interval. The step size is still 0.02, so let's go ahead and do that. I'm going to be lazy and just edit what I put in last time. I need to change this to 1. And I start at 0 plus 0.02. That's the sum. I need to multiply by the width of the subintervals, which is h, so times 0.02, which gives me 1.1520, correct to 4 decimal places. If I'm using midpoints, I have to start at the midpoint of the first subinterval, which is the average of these two, or equivalently half the width of the interval from the left hand, so 0 plus half of 0.02, which is 0.01, and it ends half a step before the end of the region. The region ends at 1, half a step before that is 0.01 to the left, so the last point would be 1 minus 0.01. The step size is still the same. Let's calculate that. And just to show you, I'm going to put this in from the beginning. So go to the list menu, go to the math menu. So we're going to add up a bunch of numbers. Now I have to tell the calculator what these numbers are. So we're going to generate it as a sequence of numbers. Go to the list menu, ops, tab, sequence of numbers. Calculator remembers what I put in last time, so I still have that. Otherwise I have to put this in. We are going to start at 0.01. We are going to end half a step before 1, so 1 minus 0.01. It's the same step size. Find the sum. Just multiply it by the width of the subintervals, which is 0.02, which gives me 1.1478. There are two things to notice here. Note that these two are much closer together. Let's go back and look at what we had last time with just 5 subintervals. It was 1.1087, 1.1916, 1.1466. The midpoint didn't change that much. It went to 1.1478, but the other two are much closer together. This is often what happens for simple functions which don't go up and down a lot. Midpoint rule is very efficient. If the function is smooth, has nice derivative, and the derivative is not too big, then the midpoint rule doesn't change very much as n goes to infinity. But the right-hand endpoints and left-hand endpoints tighten up, they get closer together. Remember this observation because it's going to be one of the important considerations when we define the definite integral. Next time we will look at an example where we do a symbolic calculation but with just a low degree polynomial where the algebra is easy.